percent nitrogen, there's air inside. And one thing about gases is that they're always expanding. That's why our balloon stays inflated. But now, what do you think is going to happen to our balloon if we put it 300 degrees below zero in our nitrogen? Any hypotheses? What do you think, Logan?
It's gonna pop.
Think it's going to pop? Do we all think pop? Think it's going to pop? Well, keep your eyes on my balloon here, because the molecules react in the same way that we do when we get very cold. When we're cold, we don't spread out. We start to come together and try to find some warmth. All of the air inside the balloon is losing energy, losing temperature, but we haven't lost any air. Every last molecule still inside of our balloon, it's just become liquid air at the very bottom. But not for long, as you see, because once it comes out into the air around us, feels good for us today. It's a beautiful day, but for our nitrogen, it's like touching a stovetop, 400 degrees Fahrenheit. That's how our nitrogen feels. Even if you add some heat to it, it boils off much faster. But I want to show you this one more time, not because it's my favorite experiment, but because this is why NASA uses liquid forms of gases when they're launching rockets. You carry a lot more of the gas as a liquid, but it's also a lot easier to transport and carry around because liquids stay together as just one unit. But as you see, that entire balloon full of gas only takes up a fraction amount as a liquid at the bottom. Then once it comes out into the warm air around us, we got a traffic jam. Once it comes out into the warm air, it regains all the energy and it boils back to life, reinflating our balloon. Now, that liquid air, it is boiling just like our nitrogen is as we speak. But instead of just blowing air into it, we're going to use our Snoopy tea kettle. Snoopy is the mascot for NASA safety, and today he's going to prove to us if it's so cold that it boils. Because typically, we think of boiling as boiling hot. Like water, for example, boils at 212 degrees Fahrenheit. Whereas our nitrogen boils as soon as it meets the air around us. Now, the reason why it whistles so loud is because liquid nitrogen is incredibly expansive. That means, as it boils, every one liquid molecule has nearly 700 gas molecules being released out into the air. And that's why it whistles so loud, simmer down, but it's also why NASA uses it as an actuator. That means that for fuel, for power, it's liquid oxygen and liquid hydrogen. But they use liquid nitrogen and that pressure to send that fuel to the combustion chamber to then get the chemical reaction started. And it's also why ventilation is very important for this element. Which, speaking of ventilation, does anybody want to bring some liquid nitrogen home with them? Anybody? My friend Logan, you want to take some home with you? Now, and what was your name? That was Raylan? Pleasure to meet you, Raylan. Now, my only question for you both is, did you want to bring home a little bit or a lot? A lot? You got it. Now, I'm going to give you some. This way you can do your own experiments, teach your friends and family about it, even start a YouTube channel. But it is on one condition, because this can be very dangerous. And so I'll give it to you as long as the lid stays closed on top of it. Does that sound fair? You've got it coming right up. I'll also put just enough. You can put some marshmallows in here. It's a great little treat. My friend Logan and Raylan, it's your lucky day because you are going home with liquid nitro. Oops, sorry about that. So one more time, because you are going home with, sorry, one more time, third time's a charm. You're going home with liquid. All right, do you think this is gonna work? But what do you think's happening? Why does it keep popping off? Exactly right. Our nitrogen boils, and that's not a problem. It's once you trap all the gas inside of it, the pressure keeps on building and building until it becomes so strong, our lid pops right off of it. Now, this is similar to rockets. Rockets build pressure using their chemical reaction. And then beyond that, they follow Newton's third law of motion, which if you know it, say it with me, that for every action, there's an equal and opposite reaction. So once they build pressure, it pushes down against the launch pad, that's the action force, and the reaction is the thrust that carries our rockets up into space. Now, this next experiment, it is a hands-on experiment. Do we have any volunteers? My friend, come and join me. I actually need all the help I can get, so if you want to join me, you're more than welcome to. Because what I have here is more of a challenge, if anything. So, sir, what was your name?
Lenny.
Lenny, pleasure to meet you, Lenny. And what I have for you here today, like I said, more of a challenge, that would be these rubber tubings here. Now, I'm convinced these tubes are indestructible. No matter how hard you try, they snap right back, but you seem pretty strong, so, see what you got. You see what I mean? It cannot be broken. Now, I'm going to help you out because now we're going to put them inside of our liquid nitrogen. Now, my friend Lenny, would you be happy if I put you in here?
Yes.
Oh, you would? Well, our rubber tubing does not share the same feelings. In fact, it's going to be very angry. But before we do take it out, do you know what time it is?
Hammer time.
It's hammer time, exactly right. We're going to use this hammer. Accuracy is more important than power. And we're going to use it, bring it down on top of our rubber tubing after a short little cryo bath. But when I told you our rubber tubing is going to be angry, oh brother, look at this. Our rubber tubing is so mad that it is quite literally fuming. You see that? Well, Lenny, we'll go ahead, bring out our rubber tubing. Go ahead, use that hammer, bring it down right on top of it, and let's see what happens. Oh, our rubber tubing is no longer very indestructible. Now, what happened here, same thing as our balloon. Well, first off, we say it's a flexible solid, so molecules have space between them, allow them to stretch, snap, and even bounce. But like our balloon, when it gets very cold and loses energy, those molecules come together, and they go from flexible into now brittle solid. Let's take it back to my friend, and if we may, round of applause for Lenny, please, our brave volunteer. But that is why liquid nitrogen is commonly used in machinery and such for shrink-fitting metals, like wheel bearings, slows them down, come together just a little bit, get some real tight spaces. And for this next experiment, I need one more volunteer. My friend, what was your name? That was Luke? Come and join me, Luke, because I need one brave volunteer to put their hand inside of liquid nitrogen. Do you want to still sign up for it? Well, you know that I could never let that happen, but we are mostly water, we're organic matter, just like these beautiful leaves here. So my friend Luke, go ahead, feel these leaves, make sure they are real, they're mostly water, and we can even grab them, they're not falling apart. Now Luke, are you left-handed or right-handed? Thinking right hand? Now I have some gloves here for you, my friend. They might be a little small, so excuse me, but here's a right hand glove for you. We're gonna use this glove. Once I bring it back out, I'll put it right on the table here. Go ahead, use that glove and grab them just like before. Just like, even that works perfect. Now, once again, it's mostly water inside of our leaves here, roughly 80-90% for our leaves, whereas our bodies, 50 to 75% water. My friend Luke, after only 3 seconds, are you ready? Coming fresh out of our liquid nitrogen, go ahead, use your glove and crush it. Ooh, ooh. Now, if you can see this, our leaves, we now have leaf confetti shattered into a bunch of pieces. Was that very hard to break? Not at all, really, right? So you can't break liquid, I'll take a look back to my friend. You can't break liquids, but in our nitrogen, they do freeze almost instantly, which turns into solids, which in true solid fashion, they do break, they rip, or they do shatter. But once again, round of applause for Luke, please. Our brave volunteer. Great job, my friend. Now, if you were to put your hand inside of liquid nitrogen, it wouldn't shatter like our flour did, but you would lose your hand. That's why leather gloves are so important. But for this last little demonstration, I'm going to show you guys something called the Leidenfrost effect, which if you put your hand inside nitrogen, it's not a good idea, but if it were to splash you, it's not the end of the world. Because keep your eyes on the tabletop here. I'm gonna pour just a little bit of it out and notice how it behaves, how it slides right over the table. See, it just slides right across the table, and that's because there is no liquid touching. As soon as it makes contact with the tabletop, it's gonna boil. And it's that gas that comes off it as it boils that acts as a barrier right underneath it, so there is no liquid touching. And that is the Leidenfrost effect, which once again, if it were to splash us, not the end of the world, but you saw what happens, put your hand inside of it. Leather gloves are very important. Now, I do know some things about liquid nitrogen, but I can also read minds. Does anyone want to give it a try? My friend Logan, want me to read your mind? Very simple. Just think of, they say today's Monday, think of your birthday. So not the month you were born, just the day. Like I was born the 12th day of the month. And you have that number in your head? Make sure you don't tell me what it is. You have it in your head? Well, my friend Logan, please tell me, do you see that number on this first card here? It is on this one, I thought it was. How about this card? And it's not on this one? Do you see it here? It is on this one, and we've got 2 cards remaining. It's not here. Last but not least, do you see it here? and it's not on this one. My friend Logan, the day you were born was none other than the 20th. Now, you see, I can't actually read minds, but I am using the binary code to find these answers. Does anyone else want to give it a try? My friend, what was your name? That was Sam? Sarah. Pleasure to meet you, Sarah. How you doing today? Doing pretty well. Now, once again, think of the day you were born, not the month, just the day. I'm also going to use the iPad so you can follow along right up top to see how it's done. Because like I said, we're using the binary code. And the binary code consists of only two numbers, in fact. That's a 1 for yes or 0 for no. And you'll also find it on electronics, for example, the power switch, that 1 for on, 0 for off. So right up top, and there's all these numbers. We got 16, 8, 4, 2, and 1. Together they equal 31. The same corresponding numbers on our cards. The very top left, we got 1, 8, 2, 16, and 4. They equal 31. My friend Sarah, have that number in your mind? Well, please tell me, do you see that number on this first card here? It's not on this one. I didn't think it was. Go ahead and place a 0 for no over the number 1. We know it's an even number. Do you see it here? And it's not on this one either. Number 8 gets a 0. But do you see it here? Oh, and it's not on this one either. 2 gets a 0. We only have 2 cards remaining. Do you see it here? Ah, we got one. It is yes on the 16. And last but not least, do you see it here? It's also here. Well, my friends, you guys share the same birthday because all we have to do now is add the yeses, add the ones together. So we have 16 plus 4 equals 20. But how does the computer say 20 in binary code? That'd be 10100 binary code for number 20. Does anyone else want to give it a try? My friend Raylan, you have that number in your head? Well, please tell me. Let me go ahead and clear the board for us. Do you see that? Oh, I cleared the board all the way. Well, go ahead and reset it. We have 16, 8, 4, 2, and 1. Please tell me, do you see that number on this first number 4 card? It is on number 4. Place a 1 over 4 for yes. Do you see it here? It's not on number 1. Once again, we know it's an even number. It's not 20, is it? Do you see it here? It's not on number 8. Go ahead and place a 0. And 2 cards remaining. It is on number 2. And last but not least, do you see it here? It's not on number 16.
So
now, once again, we have some work to do. So the only 2 numbers that appear as yes, be 4 plus 2. My friend Raylan, you were born on the 6th. But once again, binary code at 00110, binary code for number 6.
Wow.
Anyone else want to give it a try? My friend Luke, you have that number ready?